we're going to talk a little bit about securing the network. Some of the things that we've mentioned, talked about before. So, double dose doesn't hurt anything. Maybe even heard about demos, and as you know, I like to do demos. Did in the Network Plus. So we're going to talk about network security appliances, firewalls, routers, filtering, what goes on with those things. How to secure via transport encryption. So we're going to have VPNs is what we're really talking about here. How to harden networks and how to monitor networks and detect threats. Again, some of these things we've looked at before, maybe in a different context, but the way that we would do these things. So we're going to talk about, the first thing is access control lists. And what I want to do before we look at the slide on access control lists is do a little scrawl about what an access control list is. You see, I turn the ink on here. So an access control list controls access. So ACL filters, and it's going to permit or deny certain traffic at layers 3 and 4, depending on which one we have, or maybe a layer 3 and 4 combined, an IP and a port. And remember, the port represents a service. HTTP, web, 443, secure web, those sorts of things. So it's going to filter things based on layer 3, the IP address, and or layer 3 and layer 4, and I'll try to do a little demo on those too. It's basically an ordered list. An ordered list. We also have a policy, and a policy can be POLICY. Policy can be deny or permit. Deny denies everything we don't permit, and permit permits everything we don't deny. Permit's pretty dangerous, not really used a whole lot because it's easy to make a mistake there. The deny, if you make a mistake, you've not opened your network up. You've only inconvenienced people. So, if we didn't permit it, we can deny. It's going to be denied, and we'll look at why that happens in a little bit. We have two types of lists. One of them is called a standard list, which only filters on the source IP. So we can permit or deny source IPs, and we may want to permit some things and deny some other things. One of the issues, and some of you have heard this story, but we had an individual who was abusing their internet privileges. So the answer obviously is, hey, just deny them access to the internet. So we went in and put a command in to deny their IP address and shut down the internet for everybody, because the policy is deny, which will deny anything that we don't permit. So what we should have done after we did the deny IP, to deny that IP, was to permit everybody else, which would have been permit anybody else for those things. And then after that, we would have had what's called an implicit deny at the bottom, which is there. You don't see it, but it is part of it. So the standard is the source IP address. The extended is the source and destination IP as well as the port. So I can then permit users from outside to get to maybe a web server and then deny them access to everything else, using the source and the destination IP addresses to do those things. See, right from the top down, it's an order. So I got ordered list, and the statements 1, 2, 3, 4, whatever, the packet comes in, looks at, goes through the list, and the header information gets read, because the header information, we've got IPs and ports. So we're looking at the TCP and the IP header information. It looks at statement 1. Does it apply? If it's no, it goes to statement 2. If it's no, it goes to statement 3. If it's no, it goes to statement 4. If it's yes, it just does it. The old Nike, just do it. and then statement 5, 6, or whatever else is there, it doesn't look at those. So it goes down the list until something applies, and it doesn't look any further in the list when we do those things. So if none of the statements apply at the bottom of the list, the operating system has what's called an implicit deny. It's a deny any, which denies everything. We'll deny everything that hasn't been permitted up here. We need at least one permit statement. If we don't have at least one permit statement, my example of what happened by getting in a hurry, then the only thing you have are deny. And you deny, and then at the bottom you deny everything else. So we do those things. When we add statements to them, they're added at the bottom. Added at the bottom. So what that means is, if you mess up and you've got to go edit these things, you got to rewrite the whole thing. Shortcut is use Notepad or any text editor. Not WordPad because it has formatting information in it, but Notepad, which is a straight or any other straight up text editor. And then you can copy and paste them into the devices, into the routers that we're doing. Let's see, we can apply them, and we have our router, and we have the interfaces. They're applied at the interface. Put an implicit deny into the list because it's already included in the last rule. Yes, the implicit deny is part of the operating system. I just did it here to show that it is there. You won't see it, and when you look at Cisco and when you do the show commands in Cisco, anything that is part of the operating system that's the default don't show up. Only the things that modify the default show up in any of the configuration commands. But what Caesar says is, I didn't need to put that there. No, because it's there. There is an implicit deny, and I should have maybe here said implicit deny any, but we'll do that. Implicit deny. It is there. It's part of the system. You can't make it go away. So what we do is we write the access control list. It's a two-step. We write it, and then we apply it with separate commands. And we apply it at the interface either in or out. Going into the interface or coming out of the interface. So, and that means that we can have a single access control list that's applied in a couple of places. That might be necessary, might not be necessary when you do those things. So we have the apply it inbound or outbound when we do those things. And then again, we have to have at least one permit. The more specific at the top. More. This one actually does have an eraser. More specific rules at the top. And that's what this one was. We denied a single IP and then we permitted any. If we'd have done the permit any, and then the deny IP, it wouldn't do anything. And then we would have the implicit deny here at the bottom. Because the one that we were trying to deny would come in here and says, oh, permit any. I would just do that and go on. I'm not going to go look and see if I'm denied farther down the list. So they won't do those things. The kind of the order that these things are done. They are applied inbound or outbound, ordered list of permit or deny statements that we do with those things. So the control access, limit resources, the network access control list is different than the permissions because what we're doing after we get the user authenticated is we're controlling access to different parts of the network. We said that, we had the AAA authentication, authorization, which determined access, and once we determined access, what we could do. But that's what we can do on a resource, on a server. Can we use a printer? Can we edit a file? Can we read a file? The access control list is can we get from one part of the network to another part of the network. What we're doing is segmenting what goes on in the system. So when we segment that, bad drawing here, let's say that we have several different areas in our network, and maybe we have the bosses here, and maybe we have production over here, and we have payroll over here. And off of this router, maybe we've got us, the worker bees. So we'll have the workers here, or whatever we have, students. And we connect these things together. What we can do, who can get to the bosses? Well, maybe nobody. So we don't allow any of the others here. So this one would probably be an outbound deny, because if we could apply it, actually we could apply it inbound on these interfaces to permit that, to deny that, or on the outbound. The problem is if it's outbound, you have to go through the processing on the router. But by applying access control lists, we can filter or control who can get where. Who should be able to get to payroll? Maybe nobody. Maybe the bosses can get to payroll, so we would only permit those IP addresses to get there. We certainly wouldn't want the workers or the students or the production to get there, so we would deny that access when we do that. And you can do it a couple of ways. Since we have the implicit deny, if we do the permits that we have, and we did permit this and permit that, permit whatever, and then we have the implicit deny, we can write explicitly the denies, or we can just, let the implicit take control of it. Access control list specifies traffic types, and when it's applied, you have traffic filtering and edge control devices. There are also internal control devices. I don't know how LeaderQuest is set up. I know how we were set up is that we had a student network, we had the faculty network, and the student network couldn't get to the faculty network, which was a pain sometimes because when we didn't have VLANs, because you go into a classroom and you couldn't get to your home directory to get something that you needed in the class. You had to figure out how to get it to the machine that you were using. So you need to think through those things. What kind of controls are we going to have on each of those? VPNs, VLANs fix that, because you could put a port in the classroom on the faculty VLAN, and that's where the faculty machine was. The access control list, the slide that shows these things, and over on the right, the packet comes in, the access control list at the router interface, either inbound or outbound. We have statement 1. Does it match? If the answer is yes, is it a permit statement? If it is, then it's forwarded to the destination. If it's not, it goes down there into the packet drop, goes into the bit bucket. If it doesn't apply, if it's not a match, we go to statement 2. If it's a permit, yep, we move on. If it's not a permit, or if it doesn't apply, we go to no. We go on down the list until we get to the bottom. If nothing applies, then the packet's going to be dropped by the implicit deny. So what is this? It's a mechanism used to control the flow of network traffic, not to access specific resources like the permissions in Windows are, or the rights in a NetWare would be. Identify traffic which can either be permitted or denied access to the network. And on these we're layer 3 and layer 4, or what we're using, the TCP ports, depending on whether we have a standard or an extended list, or just the IP address if we have the standard list. Allow you to define a specific group of traffic and apply a condition based on the predetermined criteria, and then apply, and this is a Cisco slide using the Cisco iOS statements on the router. Applied is either an inbound or an outbound rule, and it validates the packet to determine whether the packet has been blocked or allowed to pass. I was going to, and I think that maybe less, go through a little quick one, as long as I can get it open here. And I have a network here, and we have our spanning tree starting up. I've got I think a web server up here, 2.2, and I've got a couple of resources here. So what we can do is allow one of these devices access to the server here. So last one we got 1.2 and 1.3. So I can go into my system, and don't worry about how you get to these things. But what I'm going to do is configure an access list, and we'll call it access list 1. The numbers tell the iOS, the number, if we use a number list, the number tells the operating system whether it's a standard, the source IP address and 1 to 99 are standards, or whether it's an extended, 100 to 199 would be extended. So access list 1, and we're going to permit 192.160, well, let's do host, because we have to tell it how much. Host 192.168.1.2. So, and that's all we need. And a question mark tells me what's left, and that's all that I have. This one should be applied closest to the destination, because if I stopped it from going in here, then if I had something else, like maybe an internet or a different network over here, then it wouldn't be able to go through. And I got to see what interface that is, gig 00. So then I have to apply it. Interface gig 00, and it's IP access group 1 out. Now, I didn't put a deny on the 1.3. So let's see if our works 1.3, and that was 2.2, right? And I think I've got a little web server running over there. So it'd be HTTP 192.168.2.2. And maybe I don't have a web server running. Oh, well, no, this is the one that shouldn't get there, right? Request timed out. So if routing's working, it couldn't get there. Let's see if it permitted this one. Now I know what programming I want to do here. So that was what? HTTP 92.168.2.2. So it can get there. This is the Cisco web page. So it can get there. So our access control list worked. Just a little quick demo on what they are and how they work, and that yeah, we really do have an implicit deny at the bottom of these things that will deny everything that hasn't been permitted. So ACL looks at the first statement, if it applies, does that, because, and that's what the 1.2 address did. It said, hey, first statement says I can go, so it went. The 2.2 or the 1.3 looked at that and said, oh, that's not me, and I'm now at the bottom of the list. I'm denied. So the policy, the safe policy, and most people use the policy of deny to do these things. So the access control list, an implicit deny access, is denied unless a rule explicitly allows it. And that's one that is typically going to use. Can contain only explicit allowances, is often called a whitelist. And the implicit allow is allowed unless a rule explicitly denies it. And you can think about that one. That's pretty tough, that to come up with everything that you want to deny on those things. An access control list containing only explicit denials is called a blacklist. And the packet filtering, we can use MAC address at layer 2. The IP address, the port number, and the protocol can all be used at layer 3. And generally, the MAC filtering is going to be, and we'll talk again about port security, that's where we use MAC filtering, or the common use is on wireless routers or wireless access points to do those things. So what this one is showing is Telnet's not permitted, HTTP is, FTP is not, and SSH is. So some things can be permitted, some things can be denied. Goes down the list one statement at a time until it finds something that applies, does it, and then doesn't look any further down the list to do those things. It can also be used for anti-spoofing, and Martian packets, and that's what they're called, is an IP packet seen on the public internet that contains a source or destination address that's reserved for special use by IANA. Multicast address, private addresses, loopback addresses, non-routable addresses, which would be the private IP addresses, the 10s, the 172.16s, and the 192.168 addresses, and they're called Martians. Packets with valid source addressing but arriving on invalid interfaces. It's coming in where it shouldn't be. Like maybe we have one of our private IP addresses has been spoofed and comes in on our outside interface. Shouldn't be there. Public addresses arriving from internet facing ports, but that should say private addresses within the organization arriving from the internet ports, not public addresses, because public addresses should be arriving on the internet ports. So we'll make that private addresses, and then addresses from the internal subnets arriving from ports that can't reach that subnet. They're not supposed to be able to get there. So the access control list filters those types of actions also. Some switch port security features, port security, MAC filtering, loop protection, and FloodGuard. Port security, deny traffic based on the MAC address. And this is another one. I know you've seen this one, or most of you have, and I don't think everybody has, but what can we do with port security? What can we do to protect our network at layer 2? And I guess everybody has it, but let's say that you're the network administrator in, let's say a university, and users come in and you have your machines that are configured, and you know that you do checks on them every day. You check to be sure that they are up to date, that they have an antivirus software on them, that you've done a virus checker on them, and somebody comes in with their laptop and says, wireless too slow, I'm just going to plug it in. I'm going to unplug your computer and plug mine in. Yeah, you can kind of monitor that in networks, but kind of not monitor that in networks. So we now have a device, could have a worm, could have a Trojan, could have a virus, that's in our network that we don't have any idea what kind of security is on it. Port security prevents that, and what we'll do here is, this is 03, is disconnect. Just do what they did. We'll disconnect the safe machine, and then we'll go in here and plug in the laptop. I got to get a cable here. We'll use a straight through cable and plug in the laptop, and that was Fast Ethernet 03. Since its MAC address was the wrong one, it immediately shut down the port. So now they can't get on the network. That worked very effectively. And sometimes you couldn't tell the faculty that was the case either, and they would plug their stuff in and get shut down and couldn't figure out why. But the MAC address table has a mapping of ports and IP addresses. In this case, And again, this is not something that you just, this is extra. In the configuration of the switch, it has this thing called a sticky MAC address. It's configured for sticky, which is the first MAC address that's configured on that port sticks to that port. And it's now part of the configuration. So if the switch gets restarted, power failure or whatever else, when it restarts, that's going to be the MAC address that's still associated with that port. It's a way to configure some security at layer 2. Pretty simple way to do it. So we can then keep the users that shouldn't be on the network on the port off of the port. And that's MAC filtering. Still useful. Easy to circumvent. Yeah, as long as you know the MAC address that you want to spoof. It's easy to do that. Port security or a wireless access point. Wireless access points, you can configure MAC filtering on those to where it explicitly filters, and you make a list of MAC addresses that are permitted on the wireless access points. You can do the same on your wireless router. Flood guard is something that is going to prevent flooding. We talked about SYN floods. What this does is layer 3 protection, can protect against them. It will, kind of take control, stop. What it really does is does a rate limit on the number of actions that it will allow to happen. So it slows things down so that we're not getting flooded on the situations when we do those things. So a number of ways. Loop protection. I think that let's see if we can do that. That spanning tree, which we talked about, the one that everybody loves. There's not a whole lot of configuration to spanning tree. It's just kind of there. What we want is to be able to have physical loops. And remember, these are layer 2 devices. We want to be able to have physical loops on the devices, but not have a logical loop. If we have a logical loop, then we can turn it off. Crashes the network. You gotta be in the right mode. Okay, so we turned it off on that one. I think I did anyway. Yeah, it's turning all the ports on. So one of them should be off. Okay, so you notice these turned a deep sort of green here. If I try to, and I got to see the addresses 1.2 and 1.3. Let's just try to ping 1.3. Ping 192.168.1.3. And nothing's happening because the network is now flooded with broadcast. We've got a broadcast storm going. I think that if we go into simulation mode and do that, well, let's see. Let's go in here, and it says it's timed out. And 1.3, it probably still will do that. Okay, then we've got some traffic kind of going here. So it goes over to that one, goes down. So we're just going around and around and around because we forwarded out all of the ports except the port that it came in on. If we don't have spanning tree, it just goes and goes and builds and builds and builds. And it actually would be going out more ports, and the MAC address table would be, they call it thrashing. It would continuously change when we did that. So what the loop protection Spanning tree protocol does is allows us to have that physical loop without creating logical loops. It also protects you from somebody doing a configuration, moving a wire to the wrong location. I worked with a guy that had happened. He had helped put in a network in Chicago, and they didn't do this, and somebody moved a wire. They didn't configure spanning tree. They explicitly said no. And somebody moved a wire, created a loop, took the whole network down. They had to fly from Roanoke to Chicago to fix the network. He said he walked into the network operations center, the NOC, and moved one wire, and everything came back to normal. Firewalls, any network element that uses pre-configured security rules to control network traffic is a firewall. We have a lot of those. We have network firewalls and we have host firewalls. Broad category can be split in a number of ways how we do them, what kind of firewalls that we have. We could have a simple one. We could have a server, a computer with 2 NICs that filters traffic that would do those things. So we have that capability to do that. And this one's firewall, host firewall. Typically we're going to have them both running because, yeah, the network firewall keeps users from the outside from creating connections to or inside of our private network. But if something gets in the network and is moving around, worm, virus, whatever, we may want that firewall running to protect us from our other machines. Different ways to do that. Host-based software running on a single host, Windows, and the XP was when it first started. XP had a lot of problems, and then Service Pack 2 added the firewall, activated the firewall, and automatically configured the systems for automatic updates to do those things. Network-based protects the network. It could be a firewall device, a computer with multiple NICs. Linux, any Linux machine can be a router. It has its own firewall. IP tables is the software firewall that runs on those, and it will go through it and it would do the filtering. We could do the same thing with a Windows server. You have to have a Windows server in order to be able to do that sort of filtering with it. Linux, the Linux systems can do that. A routed firewall filters and segments. A routed firewall is kind of like a router with access control lists, but we said earlier that anything with pre-configured controls on it is going to be a firewall. A virtual firewall doesn't have an address, runs in a virtual environment, and it's not going to be doing any routing. Runs in a virtual environment. It's going to protect our virtual machines, so we have that. We have those. No IP address, no routing capability on those. The filtering types of these things, we have 2 types of firewalls. The stateless are old ones. Stateless, every packet treated in isolation. We have the access control list rules that we have. Every packet has to be checked. It's kind of a little difficult because if you are allowing web traffic back in your network, for instance, you got to allow port 80 for every address in the world. Not such a good deal because some of the bad guys know how to encapsulate the bad guy stuff, the viruses and all those things, wrap them in an HTTP packet. So comes in and says, oh yeah, it's port 80, let it in, and all of a sudden we've got a virus on the network. So they're decisions based on the layer 3 header. A stateful firewall works a little bit better. It keeps track of all of the sessions that have been created from inside the network. Typically we let everything out and nothing in. It keeps track of what goes out, the connections, so that when the answer comes back, it lets the answer back in. If somebody else checks the state table, says, oh, that connection wasn't previously established, so you're not allowed in. Application layer firewalls read deep packet inspection, read at the application layer, and I've alluded to that used to do a lab, Security Plus lab, where we did a DNS spoof. And when the headquarters put in their new firewall, and we did a lab for the first time, it fixed it for us. We did the deep packet inspection, said, oh, you've made a mistake. You're not going to this other place. The DNS is wrong, and fixed it. So they can do a lot more. They actually read the information that's in the packet itself. Much better. This is a stateful firewall process that we talked about, and this one goes from right to left. I usually draw things from left to right, but a connection request goes to the stateful firewall. Does my access policy allow this packet to go through? And the answer is yes. So it goes out to something, to a service out here. When the answer comes back, does this packet match an entry in my state table? If the answer is yes, then it comes back in. The answer comes back into the to the originating source. If the answer is no, it's going to block that connection. The DMZ, the demilitarized zone, is an area where we allow everybody to get to a few resources. So the DMZ would probably, a web server would be in the DMZ, maybe an email server, maybe a database server. And when we talk about web servers, particularly if you're selling a product, it's really handy if everybody on the internet can get there to buy the product. So what we allow is for everybody to get to some services. And the some services would be filtered based on the TCP port numbers that we use on those things. And you see the term there, bastion host. What we also are going to do is to eliminate as many, or shut down, disable all of the services that aren't required, because what we want to do is to reduce the attack surface of the machine itself. A couple of different ways, actually, I guess there's 3 different ways here to do this. One of them, over here on the left, bastion host, is to just simply set it out on the internet. We're not going to do any filtering. We just set it out there and turn everything off that we can and check it to see if it's been compromised. But we have that. We have it there. The other one here is a 3-legged firewall, or a 3-connector firewall, 3-interface firewall. We have the firewall here filters the stuff to the DMZ. Maybe the web server out here allows anybody to get to port 80 on this particular device. And then we have filtering going into our private, our trusted network. And that would not allow those connections to take place. The one at the bottom there, the safest, most expensive, is a dual firewall. We have the outer firewall, and if something gets through, then we have the inner firewall to have more protection. So we have those. The firewalls generally are going to be the NAT, well, not generally, they're going to be the NAT devices also when we configure those. We're going to have the filter list, and we'll have NAT devices on them. A little caution up here. The small office, home office routers have a little checkbox that says DMZ host. It's not a true DMZ. What it does is opens up all of the ports on that device. It doesn't isolate it like a true DMZ here. So that's just a little warning, and that's out of the book. The book has that warning, so it's something that you can take with it. And how do we manage these things? We have this in-band and out-of-band management that's used on them. In-band, SSH Telnet. In-band, we use the same connectivity as the data is on. So in-band, we would Telnet to it, SSH to it. We would use the IP network, the one that the data is transmitting on or moving on. And what's the issue there? Somebody might intercept the connection, or be able to compromise and get into the system and do their own modifications, do their own management. And out of band is might have a modem, a dial-up, a serial interface, a console cable where you have it directly connected to a device, to a serial port on a device, is going to be an out of band. So it's not using the same medium as the data is transmitted on. What we may have, network access, the guest network, a separate network with only has internet access, similar to the DMZ, and I've alluded to that. That's my idea of bring your own device and being able to get on the network. That, yep, the network that you can get on only takes you to the internet. That way you don't really have to worry so much about somebody corrupting your private network that has all of your data and the business, essentially. The data is the business when we do those things. Posture assessment ensures that the client meets security rules and there is a quarantine network. And then the agents run at the startup, the persistent, the non-persistent, and the agentless. Persistent runs at the startup, the non-persistent during log-on, and the agentless Active Directory. I want to try to, because I've got a thing that will take a break. Okay. Somebody had an update for me that I don't want right now. What I have, and this is the virtual machine again, is a Windows Active Directory server running here. If I can get back into it. And it has, I hope, on it, this thing called the Network Policy Server. And what the Network Policy Server does is allows us to configure it, and we'll just look real quick, network access protection, the system health validators. If I go in here and look at the properties of this thing, configure, what it does, and this one's old, you can see it says Windows Vista and XP. Use the settings below to define the Windows security validation. So it's going to check to see if the firewall is enabled on the device. Does it have an antivirus application? Is it on and is it up to date? Spyware protection, on and up to date. Does it have automatic updates configured? So it's going to check that when the systems come on and deny or do whatever we say to do, either deny or maybe put them on a remediation network where they can bring themselves up to date to do that. So, firewall rules, I'll leave that one up, you can look at it. And this is just what we're going to do. We're going to allow some things, and we're going to permit anything, the source and the destination, and the port numbers. When you start writing access control lists and firewall rules, I found that if you write them in English first, what you want to do, and then go with the protocols and the IP addresses, it works a lot better rather than trying to start out with the IP addresses and the protocols that you want and the port numbers that you want to permit or deny. Question? Well, let's go ahead and keep going. This is kind of what a firewall rules would look like. First, and then anything coming into the interface would start with 1, 2, 3, 4 on down the list. We've got 2 2s there, but 1 is allow an IP. The destination and the port we're going to. The first 2 we're going to a web server, and then to 443 to a secure web server. And then DNS. DNS is always handy to have. And then down at the bottom, there's an explicit deny. If it's in Cisco, it's going to be the implicit deny. And Cisco uses permit, the term permit, allow. I think this probably is an IP table because Linux uses that. Intrusion detection and preventions, IDSs and IPSs. Intrusion detection systems and intrusion prevention systems. The difference is IPS is a passive that logs intrusions. IPS, prevention, takes action. It can do things other than just inform you that something took place. They are signature based typically. looks for the telltale signs of known attacks, and they have to be updated regularly, just like an antivirus software. So we're going to have signatures on those things. We're going to have other ways to look at them because they can look at abnormalities also. Stateful protocol analysis looks for an abnormal protocol use. And a protocol, a protocol is being used in a way that it shouldn't be used, like the HTTP to deliver a virus, something like that. So stateful protocol analysis, these are the three ways that we can get those things. And then anomaly-based or heuristic. It looks for unusual behavior patterns. Problem with that, the second bullet there, you got to establish a baseline. You got to know what a normal pattern is before you can have an abnormal pattern. It's just like baselines, any baseline on a network, baseline and performance. You need a baseline so that you know what abnormal is. How do you know what's abnormal until you establish normal? Number of connections, the processor utilization, how much data are you using, what's the bandwidth consumption? All of those things you have to determine normal. Same thing with these. What's a normal and what's a not normal for attacks? The wrong way. And this, I think we've seen this before. The true positive, true negative, false negative. A true positive, an attack occurred. The IDS recognized it. A true negative, the event was benign and it didn't say anything. That's a good thing. Nothing bad happened and it didn't tell us that something bad happened. A false positive, something not bad happened and it said, oh, we've got a problem. But the IDS mistook it for an attack. The damaging one, the real damaging one, is a false negative, where we had an attack, but the IDS didn't detect it. It mistook it for the benign behavior. So somebody has now attacked our network, and we don't know about it. And that honestly is not that unusual. I'll go back to the attack at Home Depot where they were stealing credit cards. The reason I know is because my credit card was one of them. And they didn't know that they had been compromised. And they didn't know for like 18 months that they'd been compromised. So people that are good are really good at doing this, are really good at doing this. IDS, IPS, and where should they be? The IDS here sets off on the switch and monitors what goes on. We're going to have to, since it's a switch, we're going to have to use a port mirror so that it can see that traffic, but yeah, we can do that. It can sit there, doesn't have to have an IP address, it simply monitors. The IPS over here is in line with the data. Choke points are a good place to put these things so that we can monitor what goes on. So it's right after stuff comes through the firewall, the IPS is going to take a look at it. Then it's going to go onto the corporate network. The one at the top there, where they are, what they are and where they are distinct. We have the NIPS, the Network Intrusion Protection System, the NIDS, the Network Intrusion Detection System, and then the HIPS and the HIDS, the Host Intrusion Prevention System and the Host Intrusion Detection System. An open source IPS IDS is Snort, if you ever want to play with one. It's a command line configuration. They've got configuration instructions, but you really want to learn how to do something, do one of these things that requires the command line. It requires you to get in and actually do it, not a I prefer the clicker, the GUI clickies, but I've learned the most when I've had to go in and do an open source and actually configure them. Honeypots and honey nets are intentionally attractive, and I'm looking. I got an address, at least I think I wrote it down, an address of a monitor. Yeah, honeypotproject.com. What they do is monitor attacks. What they do is set something up outside in the untrusted internet that they want to be attacked so that they can study the attacks. So let's see if we can get there. I told you I got too much running. HoneyNet. .com. Now, oh, I spelled it wrong. H-O-N-E-Y. That's probably why it didn't find it for me. So we go down here and look at the real-time attack map briefly, as long as it starts going here for us. Yeah, we have attacks. You can see attacks going on, and this is what's being attacked. So that we have the attacks going, and over here it looks like these are mostly SSH brute force attacks. So that's what they're setting up. They're trying to study the attacker's methodology. A honeypot is an individual device, and this goes back to the Cold War days for those. And the HoneyNets are a network of honeypots. So a honeypot is a decoy system, weaker flawed security. One of the tricks about a honeypot is you can't make it so weak that they suspect that it is. What you want to do is, or what the objective is, to study the techniques that the hackers are going to use. HoneyNets are a network of honeypots used to study the attacker's testing, and in the past criminal investigations, except courts have generally ruled that that's entrapment and they can't use that information. May have legal issues, particularly if you try to use it to prosecute somebody because of the entrapment issues that are available with it. An application layer security, application layer firewall, web application firewall, or a WAF, these things are more specialized when we get into them. They look at web traffic, identifies and blocks malicious traffic. A lot of applications are now using HTTP in order to execute the applications. Some of them are using HTTP as a wrapper. And a wrapper is something that goes around it with something inside it, kind of like a wrapper around a candy. When you open the wrapper up, or it gets to the destination, the HTTP wrapper is taken off, and you might have a Trojan, a virus, or something like that. So a content filter, it could be a web filter, a spam filter. A web filter is a content filter. The web filter is going to filter where we can go to. One of the things that is used as a web filter can be a proxy server, because we can filter inside of it, an outgoing proxy server, what addresses they can go to. We can filter on names, a lot of different filtering actions. And you can also cache so that you get the stuff faster. When we had I don't know, we probably had about, a 64K connection, whatever it was, and 300 students, we used a proxy server. The first one to go, because in a class everybody goes to the same site to do the same things out of the work. The first person got the information very slowly, but after that it popped right up because it didn't have to go any farther. They didn't have to go any farther than the local network when we did those things. This is from the internet. A web application firewall is an application firewall for HTTP applications. It applies a set of rules to an HTTP conversation. Generally, the rules cover common attacks such as cross-site scripting, SQL injection. Proxies generally protect clients. WAFs protect servers. Web application firewalls generally going to protect servers when we do those. Another, and this is item after item after item, load balancing. And this is a situation that, maybe we need to increase capacity, but we don't have the ability to upgrade. We don't have the money to go buy new devices, and we have some other devices that we can use. So what it does is distributes the load to the slower components so that everybody gets used a little bit. Can increase the reliability, because if one of the devices goes down, the other one is up. in these things, a lot of times you can have an active-active arrangement, or you can have an active-passive. The active-active is a situation where everybody is running, and if one of them goes down, the other ones pick up the load. An active-passive is one of the devices is in standby. It's just sitting there doing nothing, waiting for the first one to fail. So active-active and active-passive are the two different approaches to load balancing. How do we do this? One of them is round robin. A request comes in, the first request comes in, goes to the first server. Second request, second server. Third request, first server. Fourth request, second server, on down the line. You can have a weighted round robin. If we had in these servers, one of them had twice the capacity. The first request goes to server 1, twice the capacity. Second one to server 1. Third one to server 2 when we do that. So we can have round robin, weighted round robin. Typically, you're not going to look at load because that takes quite a bit of processing to do that. So load balancing, and we have a load balancer to do that. Web balancing is one of the typical ways that that's going to happen. If we did that, and we have the web here, we have a web server here and a web server here, they need identical content. Identical content on these things. So if we update one, we need to update the other one because, request comes in and goes here, next comes in and goes here. HTTP is one of those, it's session oriented. It's not a, it is connectionless by nature. TCP is what makes it connection oriented. So these things also have that it's going to keep a record of the IP address, and it's called affinity. I don't know if I spelled that right or not. Affinity, so that if this IP address initially connected to server 1, the next time it's going to connect to server 1 so that it maintains a continuity there, and it's called affinity. An affinity for that particular device, I guess, in one of the crazy whatevers we do. Load balancing techniques for these SSL acceleration secure socket layer, we offload it to some other device to do the security processing. Data compression, and that's one of the ways that we have gotten everything to be a lot faster, is because of the data compression. And that's even in the dial-up days when we went from 33K to 112K to whatever we wound up with it, I don't remember. A lot of it was the data compression algorithms that ran. Health checking tracks the functionality of the servers. TCP offloading, TCP buffering moves the resource-intensive operations to other servers. And you guys that are gamers, that happens in the high-level video cards. I think they have their own processor, so that the video gets offloaded to the processor on the video card to do those things. Priority queuing. Some traffic gets priority, quality of service sort of arrangement, so that the most important things are going to happen first. The things that can't stand any of the delay are not going to get delayed because they're going to get into they're going to get going into the systems to start with. And then content caching, store the most frequently used pages. Proxy servers will do that. And again, in our classrooms, you go through some of the courses. Everybody goes to do this. Go to whitehouse.gov, and of course they'd all go to whitehouse.com, which at that time was a porn site. And the first one to go there, went at the 56K, and it was pretty painful. And in those days, we didn't have all of the imagery that we have today, and certainly not all the ads that we have today, because you would never have gotten a web page loaded. So the first person was slow, but through the proxy server, when it came back, it got stored. It got cached on the proxy server. The second one went there and said, hey, this is really quick for the rest of them, because it's now cached on the proxy server itself to do those. Scheduling, and this is scheduling for the balancing. If we try, or for the for the load balancing, if we try to balance in that one server is busier than another server sort of arrangement, it's going to add complexity. You could have a random assignment, round robin, I think is typically the way. I know that's the way that Microsoft load sharing works, is that you go to the first one and then the next request goes to the second one, to the third, to the third to the first one, the fourth to the second one if we have two. And it uses affinity so that if you go out and then come back, you're going to go back to the same server. Web applications, session oriented, and that's why we have the affinity for these things. So we need to use the same server, or each of the requests is going to look like a new session. Again, affinity load balancer tracks the session based on the IP. Persistence, and they do use session cookies on the devices for these things. The types, and we talked about this, active for load balancing. Two servers, both are online. If there is a failure, then the others take up the slack. They take up the load to do those things. Active passive, failover nodes, and active passive. One of them is running, one of them's active, and one of them's passive. The hot standby routing protocol, I've been talking about servers, but you can do the same thing with your default gateway. And I think we looked at this a little earlier maybe, but if we have two routers here and we have this protocol, and there are two of them, and we'll call it HSRP, which is the Cisco Hot Standby Redundancy Protocol. We have a virtual, lots of virtuals going on, a virtual IP here, and a virtual MAC. And I think the virtual MAC is a really big deal, because if it didn't have a virtual MAC address, one of them goes down, then we got to wait for the MAC addresses to time out in the MAC address tables on the individual machines. So what this has is one active and one passive router, and the virtual IP controls which physical IP. So we have the physical IP on these things, which physical IP the information gets sent to. So we're going to this one. It's going to go out and do its thing, and then whatever else. It goes down, it breaks, it then automatically changes the path to the standby. It automatically comes up, it becomes the active. So we have a passive active situation here in order to do that. So that, our internet access is not impeded after that happens. Proxy servers, I've talked about them and alluded to them. There are, 4 different types here. The forward proxy, the transparent proxy, the reverse proxy, the anonymous proxy. The anonymous proxy out on the internet is where you anonymize your surfing or whatever else. But I would say, why are they free? Because not many people are doing things for nothing out there. So if you use anonymous proxy, just be careful about them. A forward proxy is one that we would typically use inside of our network. We would have our proxy server here. I don't like the pink so much. And we would have us here, our workstation here, and we'll have our internet out here, and we have our firewall here. There's a couple of things that you can do with this. One, we would configure the browser so that when we go to www anything, it goes to the proxy server. Proxy server then goes through the firewall to the internet with a new packet, a new IP address. So it uses its IP address. It rebuilds the request. So it does a rebuild, new data packet. One of the things for security that you can do is you could just only permit the IP address of the proxy server through the firewall. Don't let all these other guys out here go directly to the internet. So, little security thing here. Goes to the internet. Answer comes back through our stateful firewall, and oh yeah, we have that in the state table, goes back to the proxy server. While it's on the proxy server, we can run a virus checker on it. we can do a lot of checking on it. And then it rebuilds and sends the new packet, which is the answer, back to us. We could also do filtering here. We can have a list, F-I-L-T-E-R, we can have a list of IP addresses that are forbidden. So we could have the no IPs here. We could have the no words here. Lots of different things that we can filter on a forward proxy server. Transparent proxy is the same thing, except that instead of doing the explicit configuration of where in the internet configuration information on the machine you explicitly tell it to go to the proxy server, this becomes essentially a man-in-the-middle attack, so that it intercepts all the internet traffic and does the proxying for you. A reverse proxy goes from outside in. So we have, and we used that one time, we had our router firewall here, we had a reverse proxy here, and we had a server in here for a student server where they would deposit homeworks. So if they did them at home, we're not going to let these guys come onto our protected, our private network. What they would do was connect to the reverse proxy. The reverse proxy is allowed into the network. It would connect to the machine that they wanted to deposit their homework from home to be on time, and then send it, yep, we got it, sort of arrangements. But a reverse proxy goes from outside in, a forward proxy from inside out when we use them. There were a number of things, and I'll tell on me and my lack of ability in child rearing, but I used to use a proxy server for my son when he was a teenager, because teenagers and boys seem to be a whole lot worse. And I don't know, I never had a girl. I say a whole lot worse than girls. I don't know the answer, but could filter what he did. I could go back and look and see where he had been. You can do all of those things. We used to use that, and you could always tell if somebody was doing something that they shouldn't, because if they got to a porn site and it was an accident, you're there for about 2 seconds. And then you get these guys that would say, oh, I got there accidentally, I didn't mean to. Well, you've been there for 45 minutes. But proxy servers are one of the things that we can use on the network to do a number of things with them. Unified threat management is something that what did the kid, you mean? Is something that we can use to combine all of these configurations. And I don't really have one, but I have a sort of a one. How's that? Let's see. If I can remember the password to it. And this is not it. This is SNMP. What I want to do is, let's see, it will actually connect to I think it's still running, a router that's running. And what a unified threat management does is manages all of those things centrally. This software is pretty old, but it's called a Security Device Manager, which was used to manage firewalls. So what we can do, it can monitor, or we can configure with it. We can monitor it here. We get CPU usage, memory usage we can look at. And we're going to talk a little bit later about interface monitors. We can look at the interface status if it will wake up. So we can do interface monitoring with it also. We can also do configuration in here. We configure the firewall, the access control list. We can configure the VPN. We can configure NAT. we can configure the intrusion prevention system. We can configure, I want to see if I did. No, I didn't. Signatures, let's see. Yeah, this one doesn't have it. You have to get these from Cisco. So we can configure the intrusion. We can configure quality of service. We can configure network access control. And then we can keep going. Router access, DHCP, DNS, access control list editor, URL, local pools, router poisoning, configuration management. So this isn't one of the modern ones, but it's kind of one of the early unified threat managements and all the things that are there. Firewall, the IDS, IPS, content filtering, access control list, network-based malware. We had the IPS, IDS on those things. Proxy server, that wasn't there, but that would be part of it. It didn't have a proxy server running on those on that particular device. A VPN endpoint, network access control, posture assessment, and industry-based regulatory compliance checking. So what a unified threat management does is all of the things that we've talked about combined into a single management device, so that we can have and do those things. So we're going to talk about cryptography and that thing that we all love to hate, the OSI model. SSL and TLS, secure socket layer and transport layer security. Secure application protocols, Wi-Fi encryption standards, VPN technologies. A lot of things, a number of them you probably already have used, have configured about these things, with these things. The model, the OSI model predates cryptography. The upper layer encryption, HTTPS, and if you remember that the presentation layer was responsible for security, responsible for encryption. We're not always going to do that. HTTPS, some of them we are. We're also going to do a lot of it at the lower layers. And when we can do that with tunneling at the lower layers, we encapsulate the non-secure protocols inside of a secure protocol. So we don't have to develop as many new protocols to do that. We can go securely. And that's what HTTPS is. It's HTTP, the insecure one, that's wrapped up in security. We need protection for each protocol if we do it at the upper layers. The lower layer encryption, WPA on a wireless access point, WPA on a WAP is an example. VPNs are an example of that. Everything inside it is going to be secured by the VPN itself. Potential problems for that, got it, Don, thank you. Potential problems for that are network headers, traffic shapers, content filters. VPNs may break some protocols. The network headers, the things that go on these things, and we're going to look at what happens with them. SSL, secure socket layer, and TLS. If you go through this, and you can go look up the history of these things, the secure socket layers, SSL was versions 1.0 to 3.0. TLS, transport layer, is 1.0 to 1.2. It's the successor to secure socket layer. They do the same thing, but TLS has a more extensive cipher suite attached to it. Some of them, as they are classified as layer 5 and 6 for these things. So 5 would be the session layer and 6 would be the presentation layer. Certificate-based, we have the asymmetric key, the symmetric bulk encryption, the one-way or dual authentication. What we're using here is the certificate in order to authenticate one device to the other device. We can also use them to authenticate users with the smart cards and those kinds of things that are available. They have certificates on them, and that's how you get identified with them. The authentication in security may be one way, it may be two way. It may be the server authenticating EAP, let's see, EAP that we use for the 802.1x was a one way that the server authenticated to the client didn't authenticate to the server. So it could be one way or it could be two way. Two way obviously is going to be better. And then we have the Ch5 suites, which are the algorithms that are going to be used. And they're going to have an order of preference. We start with the strongest set and work our way down until we come to a set that is available in both of the devices. Applications here, and that's something I want to look at before we go any farther. I did and I think it worked out, a Wireshark today to look at a couple of things in this area. Let's see, and this is called TLS, Transport Layer Security. What I have here are a bunch of things, and we can just filter out, just look at TLS. So TLS, and these are all 1.2. 1.3 is the newer one. I had some a little bit earlier that were 1.3. I think those were at Google. So we have the client hello, the server hello, the certificate status, the server key exchange, and the server done. So if I go down here and look at the TLS, and we'll probably make a mess out of it, but the handshake protocol, the certificate service, the server key exchange. So we're doing a key exchange down here, and Diffie-Hellman should be a term that we heard a couple of days ago. So this is going to be a Diffie-Hellman. We're not going to go through what's in here, but yeah, we have this handshake. The client hello, I wanted to look at the algorithms, the signature algorithms. We also should have some encryption algorithms in here when we look at that. Oh, here we go. The Ch5 suites. 19 different combinations that are available to it. And some of this should make sense. All of them are here. We have AES 256, AES 128, SHA-256, the secure hashing algorithm, RSA with AES on down the line. So they'll report all of these things, and then the client and the server, the two ends, will agree upon one of the Ch5 suites, and the Ch5 suites has the encryption and the hashing algorithms all together in it. And when that happens, then they're going to, we got the certificate exchange here, certificate status, the server key exchange, and then the hello's done. The hello is when they're going to do these things. I did one, let's see if I can find it, 34. I did one with leader quest, so you can see, if you care, what happens when you log on to the leader quest. It was a 34.233, and yeah, so you can down here it says learning.leaderquestonline.com is the client hello, and then when we do the exchange, we got a bunch of gibberish going on. So the handshake goes on, and then there's some application data that's encrypted. I think that was one probably when I was logging in. The encrypted data application here, the length, the TLS, transport layer security, all of the TCP stuff up here, very readable. So TLS, the protocols that we use do all of the exchanging that's necessary to certificates, identify themselves to each other, get the public certificate, do the certificate exchange, the hash exchange, so that we have the encryption. We have the symmetric key in order to do the encryption, but we use the asymmetric, the Diffie-Hellman, the key exchange will be going on with this. So SSL, again, more of the different applications. HTTPS, HTTP over SSL, or TLS, port 443. It is HTTP going across there, and then file transfer protocol secure. You got FTPS and SFTP. Email, SMTP, Simple Mail Transfer Protocol, is sending. POP3 and IMAP are receiving. SNMP v3 is a secure one, and then EAP, Extensible Authentication Protocol, TLS, and then SSL VPNs. And SSL VPNs are pretty popular because port 443 is typically going to be open on a firewall. You don't have to go and do more configurations on it. The SSL, and this is just kind of about what goes on, nothing really magic about this. The one at the bottom, the web browser goes through an SSL accelerator, which is one of the things that can accelerate what goes on, because it's going to be doing the encryption and the decryption instead of the firewall itself. And the firewall typically, or the router, we can do this. We can have an endpoint. A router can be an endpoint, or a firewall can be an endpoint for them. But we have the decryptor, SSL, packet inspection. One of the issues that happen is if an encrypted packet is allowed through the network, the firewalls can't read those because they're encrypted. And that's where is the encryption and where is the decryption. There are some decryption devices, and they say, they could have some issues there depending on what you allow to happen. Do you allow users to use their private emails? Do you allow them to do their banking from inside? If you do, and you use an encrypting and a decrypting device, where is it secured and where is it not secured? What can they do? What can't they do? What can anybody see? Secure Shell, SSH, is designed to replace Telnet and RLog and remote login. It includes file transfer protocols. SCP is secure copy, rsync, and secure FTP. We'll take a quick look at this. Is a Windows secure copy that I use to upload and download stuff from a website that I do. We have SFTP. It's using port 22. The host name, if we're going to, that's not the one that we use. We could use secure copy for this, or we could use FTP. And FTP, we'll go in and pick the type of encryption that we're going to have, the host name, the username, and password. And in this one, we have the host name, which goes around the world, and port 990, which is the one that they happen to be using, and then the encryption that we're using. But I'm using an encrypted FTP, FTP running through a transport layer security end-to-end connection for secure connections to this. And the company actually required everybody to do that, because if you just use the regular FTP, it's plain text. Anybody that can intercept the data can read what's in it, because FTP, everything shows up in the data. You can read those things. New protocols. These are new protocols, not old tunnel protocols, and they use the public key cryptography. X.509 says only one option. X.509 is the certificate standard. What's in the certificates, the ones we looked at a little bit earlier. Secure email, SMIME, Internet Mail Extension. That kind of is a Microsoft thing. If you try to use the X.509 and the email signing and those sorts of things with the certificates, let's say go to Google on the web interface, it becomes difficult. You kind of can do it and you kind of can't do it. If you try to use signed emails on your tablet, you kind of can do it and you kind of can't do it for those things. So SMIME supports the use of this. It supports email signing, and I don't have a current certificate, or I'd show you what those look like. PGP, pretty good privacy, was the first open source encryption and certification software that was available. He actually got in trouble for it because it was considered a crime at the time to do that. He also exported it to a lot of countries where the U.S. had export restrictions too. It was designed, I think the book says, for chat boards. Really was designed for people in third world countries that were being persecuted for different things that they might have been doing. It is a really good, it was bought by, it's no longer free. It used to be free. It's no longer free. It was bought by Symantec. They own it. Instead of using the PKI, and we looked at the Web of Trust. Web of Trust, you give whoever you want to have your public key. Then they can send you encrypted information. You can share it on a server. MIT has a PGP server where you can store your public keys, and then anybody can go get it and encrypt something and send it to you, and then you'll decrypt it with your private key. GPG, GNU, and I forgot what the rest of it is. GPG is the free replacement for PGP. You can get PGP like a 30-day trial. The last time I got for the trial, yeah, it worked really automatic during the trial period. After 30 days, it continued to work, but it was more, you had to copy stuff to a notepad or something like that, encrypt it, and then copy it into your email. It still worked, but it didn't work as cleanly as it had. Secure Voice over IP, VoIP, are some other packets that are not secure by default. So SIP and RTP, the real-time protocol, session initiation protocol, and RTP are not secure. We secure them again with TLS, Transport Layer Secure Protocol, Secure RTP, AES, and SHA-1. So the things that we've been talking about are what we're going to use in order to secure those resources. Wireless encryption, layer 2. All the data is encrypted on a wireless once we enable it. A session initiation protocol is SIP. It's a Cisco VoIP protocol, and that's why you may not see it so much. Layer 2, all the data is going to be encrypted. When we go to a wired network, we don't really have any encryption. If you plug into an Ethernet network, you're plugged in, you're there. As long as the ports are up, you don't have port security and all that other stuff that we've talked about that you want to configure on your network, you're on the network. It's not secure. It's not encrypted by default. Wireless, as long as we've configured it, enabled it, is going to be that way. WEP was the original. We know that it's flawed, extremely weak, and the weakness were in the RC4 IV, the initial vectors, because the way it was implemented, the initial vectors repeated fairly quickly, and once they repeated, you could do a comparison, and the cracking process was pretty quick. It was a 64-bit key, and in the 64-bit key, 40 bits were used for encryption. WPA Wi-Fi Protected Access is based on the 802.11i standard, which is the security standard for wireless. TKIP was stronger. TKIP is Temporal Key Integrity Protocol. Temporal meaning temporary, and that was what was added to WEP to make WPA stronger. Each of the packets gets a different key. It's a continuously changing key. AES CCMP WPA2 is considered secure. And WPA2 down at the bottom is based on the 802.11i. AES is the strongest Wi-Fi protocol that we have. Last, let's see, we're at the doing. So authentication, WPA Wi-Fi Protected Access. WPA Personal, which we use at home, probably use a pre-shared key, hashed with the SSID to create a key. Convenient, but only one key for the whole hotspot. And this is one of those, at home you probably can't keep it a secret. People come in, can I get on your network? What's the key? And you can type it in for them, or you can probably turn on the guest network and make it something that you don't care if they know what it is or not. The guest network, they're not on your internal private network. If they're on your regular wireless, they're on your private network. Depends on, you know, how much you trust them, how much you want people on there. WPA Enterprise, if you select it, it uses 802.1x using an authentication server, a radius server. I've got a video on the share on the Blogspot share page, 802.1x, if you want to look at a video. I think it's probably about 20 minutes, maybe less than that, on how to configure, how to set up 802.1x on a wireless access point. EAP TLS is Extensible Authentication Protocol, which means that we can add protocols to it in a TLS transport layer, or PEEP, Protected Extensible Authentication Protocol authentication. PEEP protects, encrypts the negotiation that goes on with these things. WPA allows the individual credentials, usernames and passwords from the radius server. WPS, the Wi-Fi protected setup, and just me, I guess, I thought that was, I read the instructions, I thought that was more confusing than just going in and configuring it. I mean, I knew how to go in and type a pre-shared key and then type a pre-shared key on the computers. Convenient, it is insecure, should be disabled if it's not in use, because it has a restricted number of digits in the PIN. They can be cracked. The newer can be cracked pretty quickly, actually. The newer devices, if it sees an attempt, multiple pins to try to crack it, it'll shut down the process. The Cisco Leap Lightweight Extensible Authentication Protocol uses mutual authentication. The clients or the servers, everybody authenticates with everybody else, and then it encrypts the web keys. It's also one of those that really is not a strong encryption. This is in here. If you want to play with a wireless access point, there is in the book a link to a number of this one to be able to configure it. You can play with these things. It's a good idea. Go look at what goes on, what kind of configurations are available to you without actually, you know, going and messing up your own wireless access point. If you got all of it, you know, no big deal, but it's something you may want to consider. VPNs, virtual private networks, is distinguished from actual private networks. Actual private networks are leased lines that we used in the past. Now we want to, and rightfully so, use the internet for connectivity because, you know, it's great connectivity. We have good connectivity, good speed for all of these things, but it's insecure. So what the VPN does is allows us to have secure connections through an unsecure medium. Virtual point-to-point connections, authentication and encryption is allowed, and we may use the internal network, and it's classified by topology or protocols. We're going to have a couple of slides on what goes on with this thing. And what this shows, the image shows, the one out of the book, a host to host. We can connect two devices together. That way the data is connected throughout the process. We can connect from a host to a LAN, to an endpoint, to a firewall or a router or a VPN concentrator in order to get onto the private network, and then all of the conversation will be encrypted from us to the endpoint. Everything on the backside in the private network is going to be unencrypted. The LAN to LAN is firewall to firewall tunneling mode, is going to go from one firewall to the other, one endpoint to the other. And what happens is you have access control lists, the word again, that when you come up to the device, to the router, to the firewall, it checks the header information. If it's going to a location that should be encrypted, it shunts the traffic off to the VPN tunnel, gets encrypted, goes to the other end, gets decrypted, and is sent to the location it's supposed to. If it's not going to be encrypted, then it gets sent out to the regular connectivity over the internet. The components, authentication, tunneling, and maybe encryption. And encryption is a maybe. You don't always encrypt tunnel traffic. You may encrypt the tunnel traffic. Depends on what your requirements are. Authentication may be the only thing that you're really worried about, that you're actually connecting to who you think you're connecting to. Maybe authentication for the certificates. Tunneling itself from one to the other, it just encapsulates the data. It may encrypt it. Again, it may not. The authentication is called authentication header, and I think I've got some images here in a few minutes. Yeah, we'll look at what goes on with those things. So the tunneling methods here, this shows the internet traffic and then the full tunnel going to the LAN server. And then, this one's kind of silly. We go through the internet to the LAN server and then we go to the internet. So we go encrypted, probably full tunnel here. This one's called a split tunnel, which you can configure. This is the traffic that is supposed to be encrypted goes into the tunnel, and you can configure your workstation for that, for split tunnel. And then the internet traffic goes through a non-encrypted means to get there, so that we're not wasting the bandwidth and the CPU cycles that are required to do those things. The VPN solutions, a number of those. GRE is generic routing encapsulation. It has tunneling. It doesn't have any inherent security with it. It's got to use other protocols. Used in other VPN protocols. Its advantage is other VPN protocols. It can use other protocols. When we get to IPsec, the hint as to what it can be used for is in the first two letters, IP. So if we have other protocols, and generally we don't, but we may need to use GRE. One of the things that it will do that IPsec will not do is to encapsulate and put into the tunnel multicast traffic. Point-to-point tunneling protocol, point-to-point packets over GRE is not very secure. Multiple protocols since then uses PPP. So point-to-point tunneling protocol is a secure one. At least it's a sort of secure one. Relatively easy to set up, is supported generically in Windows. You can do a point-to-point tunneling protocol between two devices, between a device and a firewall, or whichever you want to use. When we did these things, we actually used the Cisco client and the Cisco encryption and encapsulation for these things. Layer 2 tunneling protocol, an IPsec, is a standard, but authorization and encryption are not native. It's going to use a Radius or a TACAC server and IPsec. The encapsulation protocols, the standards, the suites, we take a shell and then we put in whatever we want. We'll put in the encryption protocol that we want, the hashing protocol that we want to use, the key exchange protocol that we need to use. So by itself, it's something that we add the components to, and hopefully if you think back when we looked at the suites that were available for that TLS, that's kind of what we're talking about. That we'll pick from, one from column A, one from column B, one from column C sort of arrangement to have encapsulation, encryption, hashing, as well as key exchange for these things. Performance hit by double encapsulation in these things. Can be very secure, natively supported layer 2 tunneling protocol and IPsec by most of the operating systems. The ones that were Windows and Mac and Linux do support it. SSL TLS, the one that we looked at a little earlier, secure, but supported mostly via third-party solutions. OpenVPN, SSTP, Secure Shell Transport Protocol, point-to-point protocol VPN, and these are going to use port 443. And secure shell typically used to tunnel single applications. The telnet sorts of arrangements, the things that we looked at, my secure FTP, the different individual applications used for it. IPsec is a suite of 3 protocols to provide CIA confidentiality, integrity, and availability. IKE, the Internet Key Exchange, negotiates and authenticates. SAs are security associations, so that we authenticate. First we're going to have the certificates to authenticate one to the other, and then we'll negotiate what's going to happen with these things. The authenticating headers provides data integrity, source authentication. This is one that, we really don't need to encapsulate the data. If we need to encapsulate it, it's encapsulating security payload, encapsulates the payload data itself. Or we can have both of them, can be used separately or together. Authentication header has a stronger source authentication, and only ESP, the encapsulating security payload, encapsulates data, and both together can be slow. Anytime we do any of this clever stuff, secure stuff, it's going to take time, it's going to take CPU cycles, it's going to take memory, it's going to slow things down. And those are the things that you've got to consider. Is in security, we can be really, really secure, but really, really inconvenient. Or we can be really, really convenient and not really secure. You've got to strike a balance between those things so that you're as secure as you need to be, but that users are not so handicapped that they can't really do their job. The negotiation, and this is a 2-phase process, phase 1 and phase 2. The first one is the security associations, and what they basically do is to negotiate a tunnel to negotiate the protocol. And then once they get the protocol, the IKE phase 2 is when the actual encapsulated data, encrypted data, gets sent back and forth. This is the phase 1, sort of the states that go on with it. Hello, I'm a router 0 support and supported these crypto suites. And the answer is I'm router 2 and accept your security association parameters suite. Router 0, my public key. Router 1, this is my public key. Each calculate a shared key, because if you have the public key from the other guy and your private key, and you put them together, and the other one has your public key and his private key, put them together, you come up with the same session key. So they create a session key this way, a number of ways to get those. This is phase 1. Okay, router 1, proof I'm R1 to do these things. So we have now done part of the associations. In phase 2, the security gateways here, peers exchange more key material and agree to encryption and security methods. What phase 1 does is establish a tunnel for these exchanges, so that they are secure exchanges. The Diffie-Hellman key is combined with the key and material to produce the symmetric IPsec key, and then they send the encrypted data along with it. But 2 phases are involved in it. IPsec versus layer 2 tunneling protocol. IPsec, only IP traffic. Layer 2 can work with any layer 3 protocol. And is that really all that significant anymore? Probably not layer 3 protocols. Layer 2 protocols, maybe, because we have a number of those for wide area networks. In the local area network, we're using Ethernet predominantly. But when you get into wide area networks, you may have point-to-point protocol, you may have ATM, you may have frame relay, you may have HDLC, a number of layer 2 protocols. So we would want something that be able to encrypt multiple layer 2 protocols to do that. Is usable over the existing point-to-point infrastructure, so fewer modifications to the existing networks. And point-to-point protocol is one of the predominant ones that is used in wide area networks. IPsec authentication relies on host-based keys or certificates. Layer 2 allows user-based authentications like radius servers. In IPsec, if you watch that video, the client machine had to have a certificate from the radius server so that the radius server could identify itself. It was a one-way. It's kind of backwards. You'd think that because the server has to authenticate to the client in that case. Newer IPsec allow additional authentication methods. So we have different ways to do this. These are the different ways that tunneling can be set up. So here we have the original packet. The original packet up here, we have the IP header, the IP address, the TCP header, and the application header. So we have all of the information, the application, and we get down, we have the header information on it and encapsulation. If we're going to use transport mode, we have the authenticating headers here, but we do not encrypt the IP address. We use the original IP address. We could also use it with encapsulation. So in this case, we have authentication and encryption and the no encryption, the regular IP address. In tunnel mode, and that was the one that went from point to point, we always draw these really cool tunnels, but in here are a bunch of routers. And one of the ones that we did last night had, what, like 36 hops in it, I think. These routers can't read encrypted IP addresses. In tunnel mode, we have authentication. We put a new IP header on it, which is a clear text IP address that the routers can read as we go across this thing. We can still use authenticating headers so that the devices authenticate with each other, and encapsulation security payload. Authentication, encryption here, and you notice that the encryption includes the IP header, the IP address. That's why we need that new IP header. We have to have something that the routers can read in order to get it from one to the other. We always draw these nice clean pipes, but in those nice clean pipes are going to have to be a lot of routers to get from one location to another location. This is something that is in the book. You can look at it. It's creating VPN connections if you want to try those. There are a number of labs in the book that you may or may not want to do. So this module actually, I think, kind of short about hardening the networks, network segmentation, and we've talked about this. That's what a lot of last night was about, IP addressing. Harden hosts and data, and harden the network infrastructure. We've talked about collision domains. No privacy without encryption. A bus, a straight up bus. Everybody connected to the same piece of wire. So that all of the stations have access to all of the data. And if we put our NIC into promiscuous mode, not only do we have access to it, we'll read it. Wi-Fi hotspots are that way. Everybody sees everything on a Wi-Fi hotspot. We should be using WPA2, the more secure. WPA2 CCMP is the one that we should be using. Broadcast domains, layer 3. Limited traffic control, broadcasters stopped by routers. And then broadcast domains, within a broadcast domain, vulnerable to eavesdropping, but we've talked about switches and how the switches isolate traffic. That, yeah, we do that, but as long as we have a switched network, we've introduced some security there. And then we've talked about some ways to introduce more security on the switches. Broadcast domains are separated by routers and optionally by VLANs. The VLANs are an administrative creation of the broadcast domains. Segmenting the networks, use choke points. Use choke points to monitor things. Choke points is where we're going to put our IPSs, IDSs. The firewall is going to be a choke point. Everybody's going to go through the firewall. If we have an IDSs, an IPS would go in a choke point so that all of the traffic goes through it. And we filter everything down. Choke points where we filter everything down to a narrow location that all of the data is going to go through with it. special network types that need to have special handling or need to be considered that maybe they're not as secure as we'd like. Legacy devices, they don't have all the security. If you go back, if you have the ability to go back and look at, let's say maybe an XP machine, they're not really secure. We thought they were at the time. Say, this is a great thing and I'm never going to give up XP, but not so good anymore. Highly sensitive data needs to have special handling, special care where it's kept. And then maybe special devices. Legacy devices, special devices, and then we bring in industrial controls. Those kinds of things need to have special care taken. Isolation maybe, special protection, since they may not have as much as we would like. VPNs are a way to do that. VPN, virtual private network, secure transmission of information from one to the other, and then air gaps. An air gap is where we completely separate, and the one down there not connected to anything is air gapped. It's not connected to the network at all, or it's completely isolated from one network to another network. How do we do these things? This is kind of what we might do. We get the public service user goes to the public servers. Here we have our remote users, remote access to the web server, the business server, maybe go to the development and test. Over here, the business partners go to the business partner service. So we can isolate all of these things by VPNs, by VLANs, and just separation of services within the network itself. Securing the data, and these are like, you didn't really need to tell me that. I could have figured that one out on my own, but identify the sensitive data, because we need to take special precautions with it. Harden host devices, hosts and devices, the data at rest. Are we going to encrypt the data at rest, the data that's on the hard drives itself? Security protocols, the data in transit on the insecure networks, VPNs. Data in transit, once it leaves the hard drive, once it leaves the computer and goes on the network, we've got to use different protocols in order to protect it there, in order to encrypt it. VPNs, one of the choices to do that. And then the information subject to regulatory requirements need to be identified. And again, here we go. You really didn't need to tell me this either, but hardening network host, list of hosts, the owners and the purpose, perform updates, big deal. Really do perform updates. Disable unnecessary services. We've talked about that. That's what the Bastion hosts were about. Configure firewalls. Yep, we talked about that. Anti-malware. Disable unnecessary accounts. As people leave, you can disable or delete the account. If you're going to have somebody, let's say that, the vice president for operations left, and you're going to hire a new one that needs all of those permissions that he had to get to all of the places that the one that's leaving had. You want to disable the account, because if you delete the account, it's gone. You can create one with the same name. It's going to be a different account because it's going to have a different security ID associated with it. Disable or secure remote login. Limit who can do remote logins. Secure network applications. Have application policies and policies for temporary network hosts. Somebody that comes on onboarding and offboarding procedures. People bring on their private devices. What happens when they bring them on? What happens when they bring them off? And then we need to do monitoring on the network itself. After we've done all these things, what's going on the network? What's right and what's wrong with it? Securing the infrastructure. Harden the devices, the switches, the routers, and the firewalls. And we've talked about some of the ways to do that. With the switches in particular, with port security. Routers, access control lists, limit who can remotely access these things. Firewalls, basically just configure them. Use up-to-date firmware. Firmware do have updates. The devices, switches, routers, and firewalls, they find problems and holes with them, just like they do with Windows and Linux and Macs. They need to be updated. The iOSs need to be updated. So it's not just the computers that we need to do updates with. It's the infrastructure devices also. Secure management interfaces. Change the default username and password. And I think one of those labs had you rename the one that I never really got all of the users on, but you rename the administrator account. The administrator account was designed for initial administration. They never intended for it to be a permanent account that you use the user administrator for all of that. What you should do is make a user that fits in with your naming convention, give them administrative authority, put a really strong password on the administrator account. You can rename it and then disable it. Physically secure interfaces so that users can't get to them and use secure protocols. Network segmentation, some of the things we've talked about, VLANs, routers to segment, access control lists to control which traffic can go between different parts of the network. Router and switch security, the MAC filtering, DHCP snooping. DHCP snooping will not allow rogue DHCP servers on the network. Access control lists, loop protection, and flood guard. We talked about those, looked at loop protection with spanning tree protocol. Deploy network security systems. Use redundant systems. That can get expensive, but redundant systems is always a good thing to have. Deploy access control technologies, and then use strong encryption for these things. Use strong encryption for the WAN and the VPN connections. Perimeter networks coming into, and this is going to be that, yeah, we're on the firewall. We want to open only the necessary ports. And you may not have that many ports that have to be opened, either inside or out. One of the things to pay attention to is the traffic going from inside out, so that you can't become part of a bot army. You can filter that traffic and only allow, what you absolutely need going out. A proxy server is one of the good ways to do that, because everybody goes to the internet on the proxy server. Never transmit data using insecure protocols, and we've probably said that a dozen times. Minimize the value of perimeter and bastion hosts. Don't have any valuable data on it or significant access to the private network. Other things to consider, don't put a really big hard drive out there, because it's not going to be attractive for somebody to try to store their information if you do that. Have it only as powerful as is needed to do the job, and only have the resources on it to do the job. Kind of like the least privilege sort of thing, the least power sort of arrangement on those. Strong firewalls between the DMZ and the interior. Harden the specialized security appliances, and then monitor the exposed systems. Has somebody attack them, because we're probably not going to be running our own honey nets, although you may. There are if you want to play with it, there is software to do that. Wireless access points, harden them like other ones. Strong encryption. Disable WPS, use 802.1x, and this is an enterprise level. If you can use it at home if you have a Radius server. VPNs on open Wi-Fi. Choose unique SSIDs. You may want to disable the SSID broadcast and use MAC filtering. If you disable the SSID broadcast, keep in mind that your untechnical users are probably going to have trouble getting on, because they got to type in the SSID, and they're case sensitive. Guest networks for untrusted clients. Captive portals on guest network. Captive portals, you may need a username and password. The thing that you get at the hotel where you actually only agree to abide by the acceptable use policies, whatever their policies are, and that the captive portals are the web pages that you get to get onto to them. It could be a username and password, Could just be that, yeah, I agree to abide by the acceptable use policies. Place the wireless access point securely away from your users, high, and we used to put ours up high in the overhead on top of the false ceilings. And if somebody's standing under the false ceiling with a ladder, you kind of wonder what they're doing with those things. Periodic site surveys. One of the things to do, other interferences that may have occurred to your wireless. Also, any rogue wireless access points that may have popped up on the system. Site surveys, you just go around and check the signal strengths, what's there, what's not there, what kind of interferences that you have with the systems themselves. So this module is about monitoring. We've looked at some monitoring devices already, so we have some of those. With the transport mode and the tunnel mode in IPsec, the only difference with the tunnel mode, it encrypts it. Yes, the IP header. Yes. Tunnel mode encrypts everything and has to have a new header on it. The transport mode goes from device to device. It doesn't have that sort of arrangement. So we're going to talk about system and network monitoring tools and then how to monitor activities. And again, we've looked at some of those already, but the tools, the network analyzer captures and analyzes network traffic, Wireshark. Interface monitor, we saw a little bit of that with the SDM. You monitor an individual interface. You can do that with the SNMP devices. Port mirrors copies the traffic from one port to the other. Switches, you only get the traffic that is to you as well as the broadcast traffic. If you want to monitor, for instance, the uplink port, then you need to use a port mirror, span port, switch port analyzer is a Cisco term, in order to see the traffic from one port on another port. Top talkers and top listeners, the frequent transmitters, who's using all of the bandwidth. Wireless analyzers, wireless congestion, checks the congestion and the reception. This is an example of a couple of those. On the left here, the top talkers, and on the right's an interface monitor. It's just who's using all the bandwidth. What processes, what programs are the most popular? Who's getting the most outgoing? Who's getting the most incoming? Which servers are the busiest? Which protocols are the busiest? And then on the right, the interface monitor, what's happening on an individual interface? What's generally how much bandwidth is going out? We used to monitor all of our interfaces from the classrooms to see what the bandwidth was. Who's using all of the data? Who's trying to download movies and those sorts of things, which we really didn't want, obviously. The other monitoring tools, SNMP, management software. Real quick look here. And again, I think most of you have seen this before. We'll get rid of this thing and close that, and then SNMP, we can monitor different things. This is monitoring the workstation, the CPU load. Now, Windows is not real happy with SNMP. But down here, this is a monitoring a router. Down here, the ping time, the SSL certificate, the CPU load, it's not doing anything, so it's a very low. Memory, 26 megabytes here. The fans are normal. The CPU health is normal. So we can monitor remotely different devices. This is a PRTG, which is, you can get and play with it if you want, free for 100 sensors to use it. Logs are something that we need to do. Syslog, centrally managed logs, and if I can start it, I'll drag one over here, and if it's got any data in it, show you what it looks like. SEAM monitors and reports on logs. It's a centralized, it collects information from a number of resources. and puts them together. The advantage there is you can see sequentially what happened on different devices. This is an example of a syslog. What this is was some information from a Cisco router, step by step. So it collected the logging information. It could collect the logging information from multiple devices, and then we could see what happened at, at 1558. All of the actions that took place there, so that it helps us to piece together what happened on the network if something untoward happened, something bad happened to us. And then physical monitoring, the environmental conditions, the temperature and humidity. Temperature and humidity is a big deal for these devices when we do those things. Network analyzers, mapping a logical network structure, collect statistics on the overall activity, finding rogue systems, network errors and congestion, detecting unusual packet characteristics, monitor special traffic types, detect network attacks, reverse engineer proprietary protocol structures, and reverse engineer updates so that we can attack the unpatched systems. Find and capturing the data from specific packets and loading potential vulnerabilities. Verify network security device functions. So these are the, and again, this is one of those lists. That's just a list of the things that can happen on the analyzers. Network analyzer, yeah, you've seen this before. Wireshark is a network analyzer that allows us to look inside the data. And hopefully by looking at the things that we've looked at, you see that, yeah, if I use security, it's just gibberish down there. If I don't use security, I can kind of make out what's in the data portion of the packet. SNMP, and we just looked at what that is. We can get a read-only or a read-write. The read-only just simply monitors things. The read-write allows us to manage devices that are SNMP capable. We have a manager, a MIB, a management information base, and then on the device is an agent that sends the information about the OIDs from the MIB to the managers. Lots of letters here again. The OID is the object identifiers. It's just a string of numbers that identifies like a Cisco Ethernet port, a Microsoft Gigabit Ethernet, a Microsoft hard drive, Microsoft processor. Different things, different number strings identify the different objects that we're monitoring with the agents on the devices themselves. And the MIB is the management information base, is just a collection of the OIDs. SNMP, a bunch of stuff here, but it basically says 1 is the original, 2 improves 1. It uses quote passwords, unquote, which are a community string that's in clear text. Everything is clear text in these things. And that SNMP version 3 adds a full cryptographic security to the protocols. So SNMP v3 is in fact secure. Usernames, passwords, hashing, and encryption are all available depending on how we configure it. It's one of those, you don't have to have everything, but you can have everything if you want on it. Syslog, we looked at the syslog server, has a unique header identification, had the timestamp, the generating device ID, where it came from, the type of program that generated the message, the severity level of the message itself, 0 to 7. 0 is an emergency, and they say, well, it's not working, and I've never figured out if it's not working how it sends that. 7 is debug. Debug is a process that allows you to see all of the actions that are taking place on a device. And the message includes the generating application, the name of the service, what this message is all about, what it's actually reporting to us. The SIEM, the Security Information and Event Manager, the key word here is aggregation, correlation. What it does is aggregate information from multiple devices, allows us to correlate what goes on with this thing. And then alerts, obviously, are going to have alerts. SNMP has alerts also. Log retention and analysis tools are used with these things, but the SIEM, the Security Information Event Manager, allows us to collect a lot of information in a single place, and then we can, with the aggregation, see sequentially what happened. Did one event impact the other? Did we have a cascading events to cause things to happen? System logs. This is from a Microsoft device. Obviously, you can look at those, configure those, labs to do those. Where are you going to place the monitoring tools? Some of them are in the devices itself. Network taps, port mirrors, choke points. What are we going to monitor? And this is, what am I trying to see? An IPS, obviously, all the traffic needs to go through it. An IDS sits out to the side. Port mirrors, this says it on choke points. Port mirrors, maybe I want to monitor the upload ports from the switch in the different subnets. Large volumes of data can go through the collection systems. We monitor the data. The monitoring data is network traffic. So to place the systems in centrally locations. Ensure that the routes for the monitoring are resilient. Regulate monitoring traffic. Secure monitoring data, and consider out-of-band transmissions. This says that the monitoring data itself is network traffic. It may be. It depends on where you monitor it from. If we're using a mirror port on a device without an IP address, we're really not generating any traffic. And you can do that. We may be generating traffic. Central location, again, how do we get there? What kind of devices are we using? All of these things are going to have different factors for what the impact we're going to have on them are. The security posture itself, a baseline configuration and a security monitoring. Vulnerability assessments, we talked about those. Looked at Nessus briefly, and then security audits. What we're going to have on the devices themselves. Baseline configurations are always going to be a big deal. Microsoft has a baseline security analyzer for Microsoft devices. It's going to check, that you have all the updates. The updates, they're up to date. BellArc Advisor can help you out a little bit. Nessus home version is free, and I think it goes up to 16 IP addresses if you want to do some vulnerability assessments or vulnerability scans on your home network. And then we need a remediation policy. What's going to happen when we have a problem? What's going to happen when somebody gets on our network and they go through, don't pass the health checks? Remediation policy, and you may need a remediation network. A network that you put the unsafe, or what you consider unsafe, devices on that network and allow them to bring themselves up to your standard. Vulnerability scanners, protocol analyzer, sniffer, port scanner, Nmap, ZenMap is and ZenMap is a GUI version of Nmap, allows you to do port scanning. A network mapper finds subnet information. Vulnerability testers do that. I was just seeing if I had ZenMap available here. Let me see if I have one, or I'll do a scan and bring it in while you're working on labs. Password crackers, they are there. Check, and they can be used for things other than bad guys. They can be used for you as the network administrator to find out if your network policy is effective. vulnerability testers, web applications and databases, wireless scanner. We need to be sure that we're not getting rogue access points on our systems. Configuration compliance scanners, and then exploitation framework. Metasploit is a system, and that's in that Linux device, Kali Linux, that you can try, and you can find a number of exploits that, particularly on XP, if you can get one of those, if you want to try them, there are a number of exploits that work on it. Security audits. If you have logs, review them. If you're not going to review the logs, there's no real reason to waste the disk space to store them. Incident response reports and an incident and response teams we should have. User activities, policy compliance. We need to verify that our policies are being adhered to. User accounts and permissions, unauthorized access. You may need to audit the user accounts occasionally. Who has what permissions? And if you're using Active Directory, they've made that a whole lot easier than it used to. Used to, you had to go look at each one individually. Now it'll do a scan for you, and you can get a readout of who has what permissions. Device configurations, installed applications. We're going to compare this to the baseline. And again, baselines are important because if we don't know what normal is, what we started with, how do we know what abnormal is? Incident reports, alarms, alerts, and trends. Alarms, high priority notification. Alerts are lower priority. And trends, when we aggregate reports. Trends are from logs or from logging or from SNMPs, the things that we've looked at when we do monitoring on interfaces, or one of the ones that we did at Blue Ridge is we monitored the number of connections, the Citrix connections that we had, Citrix clients, because the users, the number of people that would come in to use that kind of started to grow and grow and grow, and we kept track of how many connections we had at certain times of the day. And we can then go to management and say, hey, we got to buy more connections. And, once you've got the data, you can do that. But trends, as bandwidth increases over time, what's causing it, look at trends. Trends can tell you an awful lot about what's going on your network. And then security, troubleshooting, things to look at. Changes in unusual behavior. One of the things about security is paying attention. What's going on the network? What's changed on the network? Suspicious performance problems. This didn't happen before, and sometimes we create, or at least I at home, sometimes I create those situations inadvertently, but performance problems, what's going on? And that's going to be one of the first indicators of a virus is everything really slows down. Unauthorized probing and eavesdropping. We're going to have to be doing some monitoring if we're going to see probing. You're going to have to look at firewall logs. You're going to have a Wireshark running that you can see what's going on. In a probe, you get a port scan. It's pretty obvious because they go in sequence. They may not go 1, 2, 3, 4. It may go like 1, 9, 2, 10, 3, 11, that sort of arrangement. But you need to be able to detect that sort of thing. Unauthorized users and devices. Keep the software up to date. Not just the operating system, but all of the software needs to be kept up to date. And before you buy software, you need to determine that they're going to keep it up to date, that there's going to be updates for it. Verify security after firmware and software updates. Did they change anything? Sometimes you get a software update, and it's probably happened to you in Windows, that, it's different. It changed a bunch of stuff, and I've had a couple of them that changed a bunch of stuff that I didn't really want it to change. Did it, either of those, modify your security? So you need to go back and check to be sure that your security is still what you thought it was. Bypassing security, only disable them during formal troubleshooting. Only disable the relevant controls, isolate the systems during troubleshooting, and then re-enable after troubleshooting. And the story I told about the German storing his movie was security was bypassed, opened a hole in the firewall, a really insecure hole in the firewall because it was anonymous access. Forgot the last thing, re-enable after it gets done. And you get busy and you forget to do things just like you do any day of the week. But these are things, checklists, you need to be sure that those happen. And relax the security only when it's necessary, and that's generally going to be for troubleshooting. Bosses may say that it's too hard. You've got to explain why you need the regulations. And the guy I told you about that did run a password cracker on his Active Directory domain and found out that the weak passwords are pretty weak. Went to the owner of the company and said, we have this problem here. Negotiation process, going with facts, negotiation process said, yep, we'll require better passwords, but we won't make them change them as often. Government, one of the places I was, I think it was about every 2 weeks we had to change the password, and we didn't get to pick them. They gave you a list of random character strings that you had to use for the passwords. So different things that will allow you to do different capabilities or monitor different capabilities on your networks.